for a minute? Or should we start now? I guess it's maybe time.
Yeah, if you're ready, Stuart, go ahead.
Okay. So I'm going to turn on my camera just to say hi. I'm Stuart. I'm Stuart Bale. I'm calling in from London, where I'm on at the end of a sabbatical. And then I'll turn my camera back off to save bandwidth. Okay, so I'm reporting from the Fields topical group. So we're a group, a kind of loose-knit group of people. You see it listed down here. And we've been meeting, we've met a few times. I mean, honestly, I think we need to step it up a little bit in the future, but we've met a few times to consider measurements of magnetic fields and plasma waves. Okay, I have a slide here that Andrea put together on logistics. So thanks everyone for joining. This is exciting stuff. I think it's really cool. And so we have this Zoom. So as Michael said earlier, please stay muted if you're not speaking. My inclination though is to let people ask questions as we go. We've got 75 minutes, and so we'll try to keep it on track. But I think if you have something that's fresh in your mind that you want to raise, please bring it up. We have David Malaspina.
Do you see my title slide?
Yes. Sorry, say again?
Yes, we do see it.
Okay.
Hi, Elena. I think you have
two sessions.
First session still open.
Yeah. Maybe Michael, maybe you can mute.
Okay, so I think I'll slowly start. And
Elena, they were telling you that your session on the other on fields is still open.
So we can hear you.
Yes, please mute yourself.
Maybe Michael, can you mute Elena?
I think she can't hear us.
She's not a participant.
Elena, you have to quit the other session.
Somehow. I'll give me a second.
Maybe someone can text her.
They still hear you.
I'm going to carry on. Okay, so my inclination is to let people ask questions as we go. I think things are fresh. We have David Malaspina taking notes, so if you ask questions, those will be noted, and we'll.
I just left that meeting.
There's also this Google Doc, and I have a short version of the link down here.
Well,
In the slides there, right? And so the Google Doc you'll see is basically a place where you can tap in questions, ideas, etc., and those will be logged and be available to the group. Okay, so here's what we're going to do. We have a couple of kind of prepared science presentations, one by Merav Ofer, and she's going to talk about, in particular, about the magnetic field, the importance of measurements of the magnetic field and theoretical challenges associated with the observations of Voyager models. And then Bill Kurth is going to talk to us about radio and plasma wave measurements. He's going to build a case motivating those measurements based on Voyager. And then I will lead a discussion as to what we've discussed, what we talked about in our working group, with an emphasis on the point that this is all work in progress. We've got more to do, a lot more to do. And that we haven't been designing an instrument or designing a set of instruments per se. What we've been doing is discussing, what are the right measurements to make, and exploring how those measurements or how instruments associated with those measurements would constrain the spacecraft and mission design. So we're trying to lay out something that lets the spacecraft engineering team design a mission that doesn't paint anyone in the corner. We don't want them to design something that precludes making these measurements. So that's kind of where we are. And now I think the next slide is Merav's. So Merav, if you are online.
Yes, I am online.
And you can tell me when to change slides and I'll move them along.
Okay, good. I started my watch, so I know that I don't talk too much. Anyway, okay, so Stuart asked me to give an overview of some of the challenges related with the plasma instrument. So I decided to focus in 3 aspects pretty briefly. Next slide, Stuart. Okay, so one, I just want to give you a really quick and dirty summary of some of the challenges, but I'm going to focus on the heliosheath. I'm trying to relate to the magnetic field. Why do we need especially a sensitive magnetometer? And then I'm going to focus a little bit on the heliopause and then the draping of the interstellar magnetic field. Okay, next. So just to set the stage for why do we need a good magnetometer, and I can just give this slide and leave because this, I think, summarizes everything. This is a recent plot from a paper from Len Burlaga that summarizes the magnetic field in the heliosheath. On the left, you can see, can you see my mouse here? Probably, right? The termination shock in red, and on the right is a heliopause, and you see the magnetic field intensity on the top panel and the angles of the field in the middle and bottom panel. And the issue of the magnetic field in the heliosheath, it's really tour de force effort that Len Burlaga and the magnetometer team do, because the magnetic field, as you can see, the intensity in the heliosheath is pretty low. It's around 0.1 nanotesla, but the error bars, or the errors, the noise on Voyager 2 is half of the signal, 0.05 nanotesla. So Len and his team, and Adam Zavos is helping as well, go almost point by point to try to extract the data and make sense of it. And part of this data is a little of a religion, a belief, because it's really tough to go, especially when there are regions when the angle vary, like lambda, those are current sheets. So you go from 270 to 90, the field intensity go really low, below 0.1 nanotesla, and you can argue that you can absolutely not trust this data. So there is a crucial, if I would argue to one single thing that the interstellar probe needs to carry, is a magnetometer that is able to measure fields as sensitive as 0.05 nanotesla, because we need, and as I'm going to argue, there are a lot of processes that probably are happening in the heliosheath, reconnection, turbulence, across these current layers that we, right now, we are unable to pin down. I'm going to show you lots of evidence, indirect evidence and work that me and colleagues have done, but this is a speculation, because at that point, if you look at this data, this radial current sheet, they're not very organized. And you're really going to, at the noise level of the instrument. Okay, next slide. So just to set the stage, to remind folks of the main questions, there is this question where these anomalous cosmic rays are particles around 1 MeV that were thought to be accelerated at the termination shock by the pickup ions that are keV particles. And as I'm showing here on the top left, from Alan Cummings data, and you can see here a before panel and a after panel. This is your diet before and after. And if you look at the anomalous cosmic rays, the red bump here, there were no changes across the termination shock. Although the low energy particles went up, the middle, the anomalous cosmic rays didn't flint. So they were not at least accelerated locally at Voyager 1. And Voyager 2 saw the same thing. And this has implications. Next slide, Stuart. This has broad implication for acceleration of particles, not just in space physics, but in astrophysics. We have one of the largest shock in this, it's actually the largest shock in the solar system. And around keV particles, not that energetic, were not accelerated. Why is that? And in fact, this is again from Alan Cummings, a plot, pretty complicated. I won't go through all the details, but you can see in the bottom panel, the intensity on the left versus time. And you can just look, for example, in the helium in red. The helium anomalous cosmic rays didn't go up in the termination shock, that is around 2005. And as the Voyager went through the heliosheath, the intensity of helium kept going up and up and up until it's dropped just before the heliopause in close to in September of 2012. So it seemed that the source of these particles are all close to the heliopause or somewhere where they're able to be transported and only peak until close to the heliopause. So it's a challenge for theory and modeling, how to explain that these particles are only peaking just before the heliopause. And it's I think, illuminating sheath for any stars, any supernova. The fact that particles on MEV, not that energetic again, are not accelerated locally at the termination shock where Voyager 1 and 2 cross, but somewhere else. Okay, next slide. Another issue that all the models, and I did talk about it in the Interstellar Probe workshop, I think 2 years ago, predict models with time dependent or not time dependent. They predict a thickness much, much larger than the observations. So they predict around a factor of 2. And the fact that you include a solar wind that vary in time that makes those boundaries oscillate doesn't resolve this issue. So all these puzzles, anomalous cosmic rays, the thicker heliosheaths, they indicate that there is a physics beyond ideal MHD that models try to mimic, and including the models, that is missing. What are non-ideal MHD phenomena? Those are turbulence and reconnection. Therefore, I'm bringing back to the need of a good magnetometer. Okay, next slide. So let me just touch quickly to some of the work that I have done, especially with Jim Drake and Mark Zwisdak in previous years, to set the stage what we try to do on investigating reconnection in the heliosheath. And you can see how challenging this is. So again, just to remind you that the sector structure, the ballerina skirt, is fill up the sky even at solar minima. And here again, this is a slide I stole from Jim Drake that shows the magnitude of the magnetic field, the angles, lambda across the sectors go from 270 to 290. Voyager 1 is at 30 degrees above the solar equator, so, and Voyager 2 is below. They are right where the Voyager crossed into the heliosheath near the edges of the sector boundary. So next slide. And one thing that we realized way back then, that the fact that the sectors are here on the top panel, I'm showing the heliospheric current sheet that is a boundary, as you all know, that separate two opposite polarities. And here we just painted it in pink and blue. As they're carried by the solar wind, and suppose you have a 400 kilometers per second solar wind carrying, you can see that the separation between the peaks is just basically 27 days carried by 400 kilometers per second. But of course, when you get to the termination shock here shown in the middle panel, the solar wind will start to slow down. And by slowing down, even whatever factor of 2 seen in the termination shock, it will make the peaks of the sector region get closer to each other. And as the radial speed will go even down and to really small values near the heliopause, the separation between those peaks is going to get really close to each other. So we started investigating it with theoretical work, with kinetic work, with MHD work. Here I'm showing one of the simulations where we try to capture the effect of the sector region. You can see here again in red and blue where the voyages are, right at the edges. This sector is carried by flows to high and low latitude, and it's paint all the front of the heliopause. So the point of this slide is to remind you that the spacecraft were embedded within sector region. They might be in and out the sector, but understanding the nature of the sector region is crucial. And whether the transport is a factor, whether a connection is happening, whatever your pet theory, or maybe it doesn't do anything, but you really need to address it. And next slide. And the problem, as I showed, the magnetometer cannot really tell us if reconnection is happening because the magnetometer has such a high noise. One of them, indirect signature of reconnection in the heliosheath, was explored by John Richardson. Here, and I'm seeing that I'm already at 11 minutes, so I'm going to go really fast. But there is a magnetic flux on Voyager 1 that is missing. So this might be an indirect indication that there is reconnection happening in the heliosheath. Next slide. And again, this is a slide very busy that I just wanted to make a point that when we did particle in cell simulation, trying to understand how reconnection will proceed in the heliosheath, this is very exciting because it's a new regime of reconnection. Reconnection, as you know, near the sun has a plasma beta, the ratio between particle pressure and magnetic pressure really low. The magnetic pressure is dominant near the sun, but is not the case in the heliosheath. The plasma beta is much larger than 1, is around 10 or 20. So it's a new regime for reconnection. And next slide. And we worked in several papers. The latest from Jim was 2017. And I absolutely was fascinated by that because a magnetic island that you're used to looking and seeing simulations that are pretty round become very elongated. This is a very different regime. And it has to do with kinetic instabilities that they shut down reconnection and they make those symmetry of islands there. So whether Voyager is crossing that or not, we cannot really tell, again, because of the magnetometer. Next slide. So I hope I gave you a view why it's important to revisit the heliosheath with the magnetometer. I wanted to touch in my last couple of minutes in 2 other very interesting aspects. We have a boundary, Heliopause, and we would like to know if this boundary is porous or not. And I'm showing here data from Tom Kremidis of the crossing of the Heliopause. And in 2012.6, in June, we started seeing some drops in the intensity of the particles in the bottom panel while the galactic cosmic rays started coming in. And I like to at least for myself, I'm visual, to imagine that you're opening the windows of your house and letting stuff come out and letting stuff come in, and then you close the window, you're still inside your house. Bottom line, in 2012.8, a little bit before, we really left the heliosphere. And you will hear more about it from a radio measurement from Bill Kurth that really cemented that fact. But that porosity, there were a couple of months when we had some porosity, and we really don't know if that porosity exists at just Voyager 1. Voyager 2 signature was very different. And again, we are struggling to understand the processes. The magnetometer at that location, the magnetic field was starting to go up. So it's less of a challenge there from magnetometer point of sakes. But if there were turbulence or a connection happening, again, you need a very, very high resolution magnetometer. Next slide. Here is just a zoom in the magnetometer. You can see that the intensities were higher, 0.4 nanotesla, that we think was outside the heliosphere. But again, there were excursion. There was a heliospheric current just before. Next slide. We put a model with Max Wisdek to try to explain it as in a reconnection happening. I won't go through the details. I just put this slide to show you the challenge of theory and modeling to try to assess the data, because again, oops, previous slide. Previous. Stuart, you jumped. One more. Previous. Yes, good. And there are other theories. There is theories by Vladimir Florinsky and others and Kremidis that this was an instability. I won't cover these works here, but again, understanding the roles of instability, so the porosity require us really high resolution turbulence and magnetometer data. Okay, next slide. And I'm going to try to, oops, previous. Yeah, previous. Yeah, previous. Somebody's playing games with me. Okay, now previous.
Sorry, I'm not sure what's happening here. My cursor is jumping around.
You know what happens sometimes when I move the mouse? Try not to move the mouse. Sometimes it's jump. Okay, next. Okay, good. No, next.
Huh?
No, sorry, previous.
I don't know if this is strange.
Okay, I will talk without an image, but try to go for the previous image. One of the challenges that we had in the Heliopause, understanding what happened at the Heliopause, is this surprise that the solar magnetic field ahead of the heliosphere was solar-like. And this, in the previous slide, what I was trying to show you that all the prediction from theories and modeling was that the magnetic field in the ISM is drastically different than the solar field that is azimuthal. We think that the magnetic field outside is inclined. So the idea that yes, you have some draping around Voyager 1 and Voyager 2, but you surely will see some difference between inside and outside. And here I'm zooming in the Len-Burlaga data on Voyager 1 and 2. Those are the angles, lambda. You can see here where Len think the heliopause is. And if you look at the angles, there is no difference between before and after the heliopause. For me, it means that there is communication between inside and outside. Somehow outside knows about inside. And not only that, the angles outside are very solar-like. The Parker spiral, as you all know in textbooks, is 270. It's really, really close to the solar-like. Okay, next slide, Stuart, very gently. Yes, great. And Voyager 1, I'm showing the left that these angles remain 270 for almost all the times at Voyager 1, and is still seeing outside the heliosphere. Whether it's a coincidence that the draping really give you these angles, whether it tells you that there is a communication that extends farther ahead of the heliosphere, it's a puzzle, needs to be understood. And again, the need for a really good magnetometer. Okay, next slide. Again, I am mentioning a work that I have done with Mark Zwisdak and Jean Drake. We try to explore that maybe a connection. This is a kinetic effect, not included in the models. Next slide. That Mark Zwisdak explored in several other venues near Earth, near other planets, that has to do with diamagnetic drifts. And if you want to, I'm way beyond my time, so I'm going to wrap it up. But you can look in this paper. This is just one idea that the field lines ahead of the heliosphere are solar-like. And they are solar-like because they are a result of reconnection in the tail. And we argue, why is that? There is a whole pattern of draping. It's like the Dungy cycle for the heliosphere. So you can go here and understand and try to read about it. But again, this comes back to trying to understand the heliopause nature. If in fact this is the case. Again, this is a basic nature of our heliosphere that we don't understand. Whether the magnetic field is affected by reconnection and draped differently in these red family lines, rather than the green. So we will need to revisit that region. I think this is it, Stuart. Go another one. I think I'm done.
And Marav, you have a question in the chat from Wayne Schley.
Okay, yes.
He says, do you know the direction of where those cosmic rays are coming inside the heliosphere? Are those of destination interest for Interstellar probe? So
the galactic cosmic rays, coming from, it's almost from all direction, isotopic. But you can ask, I can rephrase this. Which direction would be interesting based on what I said, or what I said in magnetic field to go through? And I will argue that its flanks, it's the most interesting to try to understand what's happening with anomalous cosmic rays and whether there is turbulence or a connection happening, but we can discuss it more later on.
That's an important point.
Sorry, Stuart, I went, I think by
Well,
a couple
no,
of minutes.
this was great though, Marav, thank you. Maybe if anyone has another question, we could take that now. And remember, you can put comments in the Google Doc too, if you'd like.
And I apologize for all the work that I didn't mention. I didn't have enough time to give a general overview, so I was just touch and go.
So maybe you mentioned it, Marav, but how far does an interstellar probe need to go to figure out the magnetic topology ahead of the Heliopause?
So I didn't have, this is a good point. I should have shown a slide about it. So this is a question that Bill Koth is going also to touch. How far ahead the heliosphere is affecting, if it's reconnection, it's or what else ahead of the heliosphere. And I will say that at least 400 AU. So whether we have a fast bow shock or a slow bow shock, that region is a region that is subalphanic. And so it's the signal to whatever it's happening, the heliosphere is going to propagate upstream and affect the condition upstream. So you really need to go farther around 400 to start seeing pristine ISM. And Voyagers, just to note again, are going to finish their mission way before reaching that point. So we will not know.
Yeah, 170 AU to be
right. Exactly. So by sure right now you can say we will not answer that question with how far the heliosphere or any star, if you want to put it in a bigger context, affect the medium that's surrounded with the Voyager. We need to have another mission.
Good. Okay, let's move on to Bill. Is that all right?
Stuart, do you mind if I flip through my slides? It might make it a little bit easier. So
sure. You want me to stop sharing? Yeah.
Yeah.
There you go.
I want to know if anybody's tried to scan Stuart Bale to see where that takes you.
Everyone asked that.
I did. First time I saw it. You guys go ahead. I'm going to do the same.
Okay, so I'm going to try to make a case for including a wave instrument on interstellar probe based primarily on what we've learned of the structure of the interstellar medium and its interaction with the sun based on Voyager measurements. Now, I probably don't have to repeat this, but the Voyager instruments, not only ours, but all of them, were built in the mid-1970s. They certainly were not optimized for studying the interstellar medium. But I think it's amazing what the Voyager team has been able to do with these non-optimized instruments. I'm going to talk primarily about the plasma density in the interstellar medium, the very local interstellar medium, and argue that an even slightly optimized instrument similar to Voyager's, perhaps with some enhancements, would be very valuable to add to an interstellar probe. So the two Voyager instruments started detecting radio emissions in the range of a few kilohertz as early as 1983, when they were only about 15 AU from the sun. Now, I would be lying if I said we knew immediately what was going on, but by the early 1990s, I think Don Gurnett had kind of figured out a lot of the study. This is an example of a cluster of radio emission events that last for 2 or 3 years. These started in 1992. There was a similar emission that started in 1983. And the fact that these show drifting structures suggests that the source region for these emissions occur in a radio gradient, and the source region was moving outward. We actually put together a model based in part on a model by Bronov that suggested there'd be a pileup region at the nose of the heliosphere, where there'd be a local increase in the density. And so if one can imagine a source region moving through a density gradient, you would expect that you would see a time variation in the frequency of those emissions. And in fact, even though the spacecraft were still almost 100 astronomical units from crossing the Heliopause, we could tell from these radio emissions that the density of the very local interstellar medium was on the order of 0.1 per cubic centimeter, and that there was structure in the density beyond, most likely a radio gradient. The next slide, I want to emphasize that these radio emissions are actually triggered by solar activity. So this is the first evidence that we have linking solar activity with manifestations in the local interstellar medium. And in the left-hand panel over here, I'm showing basically 3 clusters of these radio emission events. And you can see that they're spaced by approximately a solar cycle. So that's one clue. The other clue, and probably a stronger one, is that if you look at the amplitude of these radio emissions, and are labeled A and B for these 2 emissions here, they follow the 2 strongest Forbush decreases on record by almost identical times. It's on the order of 415 days. And so using a time of flight argument, you can take a merged interaction region and propagate it out through the supersonic solar wind, slow it down when it crosses the termination shock, and then calculate how far it's gone by the time these radio emissions start. And you get, I think this was the first realistic estimate of the distance to the Heliopause that was in this paper by Gurnett et al. Of somewhere between, I think, 77 and 150 AU. And it turned out to be about 120 AU. And so the fact that these disturbances had to travel that far, and the fact that the plasma densities implied were much greater than the plasma densities in the outer heliosphere, suggested that these emissions were coming from the interstellar medium. Now, I should give Ralph McNutt some credit, because I think he argued that these emissions could be triggered by solar transients probably before this Gurnett et al. Paper came out, and I don't know that he's ever gotten the credit he deserves for pointing that out. So here we are, we're on a spacecraft that's literally tens of astronomical units from crossing the Heliopause, and we're already making remote measurements of the conditions in the interstellar medium. Now, the mechanism for generating those radio emissions requires the existence of plasma oscillations. This is an electrostatic wave at the plasma frequency where they exist. These can scatter off of low frequency waves to create radio waves, freely propagating radio waves. So we predicted that there would be plasma oscillations in the source regions of these radio emissions. I don't know that we ever thought we'd be lucky enough to actually see these, but these measurements by Voyager 1, taken in late 2012 through the present, show the existence of electron plasma oscillations. This is using a high resolution instrument on as part of the plasma wave instrument with a very low duty cycle. This instrument acquires data at the rate of about 100 kilobits per second. It gets played back from the spacecraft at about 1.4 kilobits per second, and we literally get seconds of these data each week. But the fact is that this allows us to very accurately measure the density in the very local interstellar medium. We just convert plasma frequency to density over here. And the first thing you notice is that there's a density gradient. This may be that pileup region that Baranov talked about. Another model that's been suggested by Fuselier and Cairns is that this is like the plasma depletion layer upstream of the magnetopause at Earth, for example. Now, just recently, we've been able to make a second measure of the density from the Voyager 2 instrument compared to one taken shortly after Voyager 2 crossed the Heliopause. And so if we just connect those 2 points, we see that the density gradient measured by Voyager 2 is very similar to that measured by Voyager 1. Now you have to understand that the angular separation of Voyager 1 and Voyager 2 on the sky is about 70 degrees. And they're basically on either side of the nose of the heliosphere. So this argues that there's a large scale density structure, a radial gradient in the very local interstellar medium, at least in the direction of the heliospheric nose. And the other thing you'll notice in this plot is that the densities are almost identical to within the accuracy of the measurements. Now that may be coincidence or just luck, but I think it argues that the structure of the plasma density outside the heliosphere is quite regular. There's a gradient there, and this instrument has revealed that. I should say that one of the reasons we had to rely on Voyager 1 for the measurements of the density in its direction was that the plasma instrument on Voyager 1 was no longer working. It is working on Voyager 2, and it is measuring currents in the local interstellar medium, but unfortunately the flow direction is coming into the side of the Faraday cup at a fairly large angle, and the energy of the interstellar medium plasma is on the order of a few eV, which is really down at the bottom end of the energy range. So like the wave instrument, the plasma instrument was not designed for this type of measurement. And having an optimized plasma instrument would also be good. I will say that even if we had an optimized plasma instrument, we have learned through missions like Stereo and excuse me, and currently Parker Solar Probe, that the wave instrument can actually provide a gold standard for the plasma electron density. And that's been very useful for a number of missions to help calibrate the plasma instruments. So this is just a list of the contributions of the Voyager wave instrument to the study of the very local interstellar medium and its interaction with the sun. I've highlighted in red here something that I haven't mentioned, and that is that Voyager has actually measured dust out to well beyond the planets and into the interstellar medium. Allison Jane has a poster on Thursday talking about those measurements. Again, the Voyager instrument was not optimized for studying dust, but with a few optimizations, a wave instrument can be at least complementary to a dedicated dust instrument on interstellar probe. Okay, so I mentioned that with some optimization, a wave instrument could do a much better job than what Voyager has done. And one of the primary things that we would like to do is, instead of using the 10-meter rigid antennas that Voyager has to have much longer antennas on the order of 50-meter antennas and have them be very thin, that is wire antennas. This would give the interstellar probe instrument the capability of measuring what we call the quasi-thermal noise spectrum. This is something that the French group has been studying for decades. And basically, there's a peak in the quasi-thermal noise spectrum at the plasma density. So one can imagine having some onboard processing that analyzes the spectrum of this noise and just picks out that peak frequency. And then instead of waiting for an electron plasma oscillation event to come along maybe once a year, you could, at whatever cadence you choose, once a day, once an hour, once a minute, you could likely find this feature in the spectrum and know what the density is. In fact, if you model this spectrum with high resolution, a high resolution spectrum, you can not only get the density, but you can get the electron temperature. This spectrum in other missions has been modeled with bi-Maxwellian, and you can even get the bulk flow of the ions if you are careful. So the key, though, to make this measurement is have long, thin antennas, which basically means you'd like to have a spinning spacecraft to be able to carry that type of antenna. I should say that even this quasi-thermal noise spectrum would probably not work in the outer heliosphere, that is the inner heliosheath, because the temperature of the plasma is very high, the density is much lower, and an antenna that would be sensitive to this spectrum in that region of space would probably be very unrealistic. So we would suggest that maybe you would add a sounder to stimulate the characteristic frequencies of the plasma when you're in the lower density outer heliosphere. Clearly, this type of an instrument would require some onboard processing, same type of processing that's currently being done on Parker Solar Probe, and to some extent we did onboard processing to detect micron-sized dust grains on our Cassini instrument. A second dipole extended orthogonal to the first would allow polarization and direction finding capability, although with the spinning spacecraft we demonstrated that we could do direction finding with the Voyager instruments when they did calibration rolls. We'd even argue that adding a search coil magnetometer to the instrument would be of interest, because then you could look at the low frequency electromagnetic spectrum and extend above the range of the magnetometer on board. So this is a very simple block diagram. It's meant to be kind of the threshold instrument with a single long wire electric antenna, a receiver that covers from say 2 hertz up to at least 10 kilohertz. If you're going to fly by Jupiter, you obviously want to cover a broader range. A sounder to excite characteristic frequencies in the low density outer heliosphere, and a signal processor that can help you analyze the spectrum for peaks, analyze waveforms for impulses due to dust impacts. And this would be kind of the minimum instrument that one would like to consider for interstellar probe. But there are enhancements that we would argue for a second dipole antenna, which would require a second receiver channel, allow you to do cross-spectral analysis, a search coil magnetometer, and these additional receivers would probably require a somewhat enhanced processor.
Say, Bill, is there, besides stability, is there any spin rate requirements or parameters that are important to this type of antenna?
No, I don't think so. let's see, I think Voyager, let's see if I can remember the spin rate of Voyager. It took tens of minutes, I believe, to roll the spacecraft on Voyager. And these radio missions that we're direction finding on are very stable. And even if you're doing polarization, say, of plasma oscillations, you can do that with a very broad range of spin rates.
I think from the ME point of view, you want to keep about a G of tension on the wires. And so
Yeah, it's really driven by spacecraft stability.
Right, right. And so that means you need to put a little tip mass on there if you're spinning pretty slowly, but
And
not much.
that kind of brings me to the very last point, and I think Stuart may talk about this, but clearly there will be a Jupiter flyby, and there will be a desire to do planetary science on the way out, whether it's for Jupiter or maybe a Kuiper Belt object or something. And a lot of those investigations would like to have a 3-axis stabilized spacecraft, which does not go along well with a long wire antenna. So I think Stuart's come up with the idea that we could do an extension of a rigid base to these antennas to a distance of 2 or 3 meters early in the mission, during the phase of the mission where you'd be 3-axis stabilized. And then once you got beyond the 3-axis stabilization portion of the mission, you could then extend the long wire antennas and have the sensitivity that you'd like to have for quasi-thermal noise and things like that.
So Gabe Rogers, as Jim Kinnison puts in the chat, will talk a lot about this tomorrow when he's talking about control, but he actually has a question for you right now. Gabe puts in the chat, would the thin wire antennas benefit from having 2 antennas at 180 degrees or 4 antennas at 90 degrees?
Well, for both a quiet antenna and for stability sakes, you would have to have at least 2 elements to a single dipole. Having the second wire, set of wires still in the spin plane, but orthogonal to the first, I think enhances the stability of the spacecraft. But Stuart probably knows more about that than I do.
But that doesn't add to the science?
It does add.
Oh yeah.
It does, okay.
I mean, you definitely want dipoles, right? So you want them to be collinear pairs.
Yep.
Right.
And you want them to be orthogonal. So if you're going to have 2 dipoles, you want them to be orthogonal pairs. So that's 4 at 90 degrees, I guess.
The orthogonal pair allows you to do instantaneous polarization, at least in the spin plane of the spacecraft, and also direction finding.
Direction finding, right?
You can do both of those measurements with a single antenna. It's just a little bit more complex, and you have to hope that the waves are stable over the spin period of the spacecraft.
Right.
There's probably an argument for redundancy there as well, just given the lifetime of the mission and the possibility that some wire booms get cut over time, like wind or image.
I have a slide on that too. I think some redundancy or at least enhanced reliability is sensible on a mission like this.
Sure.
Please don't say cut wires. That's not a good thing.
Well, no, it's not a good thing. I'm just saying it has happened in the past.
Well, David, that's actually a very good point to bring up in the context of this mission. I mean, as we're going to talk about later in the week, longevity is a big challenge on this mission, and redundancy over time. And I imagine that the further out we go, the more that this sort of measurement is going to continue to be an important measurement through the course of the whole mission, and not just an early part. So it's a very good point.
Yeah, the long wires actually are most useful for the, beyond 100 astronomical units, I would say. But
yeah.
Can I circle back to the cut wires? Scares me too. So if we get a wire breakage out at 100 plus AU, would that not? And this is sort of a question to Gabe, I guess. Would that not be a loss of mission almost?
You would at least gain about 0.3 degrees of coning from that, depending upon the tip mass and stuff like that, and where exactly the wire broke. There's a analysis that's done in my presentation, which we'll talk about on Thursday. But yes, a single cut wire is enough to pretty much render the high gain antenna severely degraded.
Does that include the effect of magnetometer booms?
Well, magnetometer booms are their own sort of
Sure, but they
issue that they need to be symmetric as well. So
right. They provide.
Well, maybe the takeaway is that we have to consider mitigation processes in the case of a cut wire. I mean, you can fly guillotines on these, or short of doing that, you can fly the ability to retract antennas that have not been cut off to balance the angular momentum or the moment of inertia of the spacecraft.
I got to jump in here because I want to make sure everybody realizes what we're talking about. If something like that happens, say 30 years into the mission, the idea that we can rely on a mechanism that's not been moving for some 30 years to then suddenly be able to retract an antenna or even cut an antenna is a pretty interesting one.
Well, I think the guillotine can be made much more reliably than the retraction mechanism.
That may be true, but
well, so I apologize for even stepping in this, right? So my intent here was just to say that more antennas is better redundancy. That's as far as I wanted to go.
Yeah.
The rest of this is engineering details, which I agree we need to discuss, but maybe in a different forum.
Yeah, let's go on with the rest of the slide. I have a few slides here which hit on.
I think this is my last slide, so I'll stop sharing.
Okay. So what do we have left? 25 minutes or so. All right.
Thank you, Bill.
Yeah, Bill, that was great.
If everybody wants to, they can use the reaction button to clap for Bill. And we forgot to do it for Marav, or throw a thank you in the chat. It's less fun than all being together to clap for people, but I think it's good to do.
We'll clap next year. Okay, so I have, is this the good view again or the bad view? I can never tell.
Good view.
Looks good. Okay, so I'm going to just kind of summarize what we've been doing in the group, and Bill and Marav have already made the case, I think, for the measurements, but I want to come back a little bit to the case for long wires. I'll show you analysis that supports that. And then I will discuss, as Bill said, the possibility of having a kind of hybrid configuration that would be suitable for a 3-axis stabilized phase of the mission. And then I want to just underscore some of the things that we should keep thinking about. Again, we're not designing an instrument here, but we're just like trying to flesh out what we think needs to go into it and how that flows through to the spacecraft and the mission design. So, okay, so Marav made a better case than I can, but as far as the magnetic field, keep in mind it's very weak, right? So we're talking about, a fraction of a nanotesla, at the Heliopause, and that is with a lot of integration, right? So instantaneous stuff, shorter spatial scales, shorter temporal scale stuff, at least with Voyager, is really hard or impossible to do. This is a plot that was made by Chris Chen, who's taken a look at Voyager measurements in the interstellar medium and looked at power spectra. And you can see here, now look at the time scale down here, or the frequency scale. And you can get a meaningful spectrum up to, 1 million seconds or so. And above that, you start to hit sensor noise. Okay, so, this is using the 46 second data. And for reference, if you just track these 5/3, Kolmogorov-like, Goldreich-Sridhar-like spectra down to where they hit where you would expect the proton gyro scale, that the fluctuations at the gyro scale, which is where you start to see, current sheets in the absence of pickup ions anyway, where you start to see the boundaries of current sheets, is below the noise level of a modern magnetometer. This is the solar orbiter magnetometer noise level. So this is a challenge. So in addition, it's not so much as that the instruments are noisy, it's that the signal is weak. And we have to think carefully. We should be thinking carefully about how to do this. I mean, this is, I think, one of the big challenges for this instrument challenges for this suite is to try to get another couple of orders of magnitude in signal to noise for this kind of measurement. Especially if we want, I mean, if you want to integrate for days, you can do something. But if you want to look at structure that's associated with the boundaries, this is going to be hard. Okay, to the radio. Okay, Bill made a gold standard case for the radio mission. I mean, the radio mission is remote sensing. It's great remote sensing that travels at the speed of light, and it tells you what's going on long before you get there, and it gives you, and as he pointed out, if we do it correctly, if we do some direction finding, we have some direction finding capability. It tells you something about the magnetic field geometry upstream as well. Now, Bill pointed out the quasi-thermal noise spectrum. This figure on the left shows you, this is from a paper by Milan Maximovich showing a spectrum from, I believe this is Ulysses, or it might have been Wind, showing this quasi-thermal noise spectrum. So the dots are measurements, wave spectral measurements, and that peak there is at the total electron, the plasma frequency, which is electron plasma frequency, which gives you the total electron density. And if you do this correctly, if you have the right antenna geometry, it's about having a good antenna geometry, having good instrument sensitivity, and having a quiet spacecraft. You can not only measure the density, the total density, but you can measure the fractional two-component if you consider a core halo, for example, so superthermals, and you can measure their temperature ratios and their total pressure. So you can, in principle, with a good measurement, back out a lot of information about the electron populations. But minimally, you can at least get the electron temperature, the electron density. And this is, as Bill said, it's really kind of the gold standard. It's a measurement that doesn't depend so much on the absolute calibration of the instrument. It's a measurement of a frequency spectrum. It depends on the stability of your clock, which is usually pretty good. And this shows finally a plot from, on the right-hand side, let's look at this. This is from a paper by Karine Sautier, showing on Ulysses a measurement of the density, the speed of the solar wind as well. So you'll see in a few slides here that I've got calculations of these parameters, but not only can you get the electron parameters, but you can get the ion thermals. You can measure the ion thermal noise, and that ion thermal noise is Doppler shifted by the ion velocity. And so if this is done correctly, we also have the capability to provide a speed measurement. And I think, if I understand this correctly, this is the speed in the plane of the antennas. And so this would be the speed perpendicular to the spacecraft sunline, the spacecraft Earth line. So this would be the component that would be hard to measure with a Faraday cup, for example. So it's a very capable measurement if it's done right. And then finally, dust. Bill mentioned this as well. So this is a figure on the left of what a dust impact looked like on Voyager from Voyager 1, I think from a paper by Don Gurnett. And on the right shows what we were able to do, what we have been able to do on Solar Probe by measuring these voltage impacts. So when a dust particle, to remind you, a dust particle hits the spacecraft, it produces a cloud of charge. That charge cloud produces a voltage impulse, and we measure that voltage impulse. And by just counting up those voltage impulses, we're measuring the effective dust density. And we've been able to do that on Solar Probe spectacularly. We don't have any information about the dust mass, the mass or the composition or anything, but we can count, we can use the entire body of the spacecraft as a collector. So it's a very powerful technique, and we should take it seriously. Okay, so what we've been doing here in the group, we've been looking at the STM and trying to understand how it maps to the instruments. And I don't think we can't go through this whole thing here, in part because it's a gigantic matrix. But what I've done is I've broken out, so for example, we can say that the magnetometer might be a primary measurement or a supporting measurement. We can say plasma waves might be primary or supporting based on the objectives in the STM and the draft STM. So what I've done, I'm going to speed ahead here because we're slow, is I've made an open version of the STM that's got everything paired out except MAG and PWS. And so it's easier to handle, it's easier to read. And so I think, and I've left it open to the community. So I think what we should do is we should go in here, look at those objectives and make a note, say something, you could imagine doing this with a magnetometer under the MAG column. You could imagine doing this with a plasma wave system. and maybe leave your name if you're doing this too, so we can get circle back and try to get people together on this. But I think this is a good way for us to look at the overall objectives of the project and map them down to these instruments and see how they matter. Okay, so here's just, okay, you've seen this stuff before, but I want to show you now the motivation for the antenna, for the long wire antennas. And Bill discussed this already. This is data from Parker Solar Probe. Parker Solar Probe has short antennas, 2 meter long antennas, but it's in a very high density region. So this is our wave spectrum from a few kilohertz up to 20 megahertz or so. And embedded in here, it's hard to see because there's a lot of dynamic range, is a line, the plasma line, which you can faintly see through here. And below here is we have a peak tracker that finds the peak of the spectrum and follows it. And you can see that line there. That line is the quasi-thermal noise line. Occasionally it lights up kind of brightly. Those are Langmuir waves, like Bill showed from Voyager. But by and large, this is a thermal line. If you look at the spectrum of it, you can see it has a little peak in it, like that. And that's the peak that we want to capture to get the density. You can fit this to a model, and what you get from that model is the electron parameters, and you get a shot noise curve, and the shot noise is a bad thing. That is not a good thing for us. And then you can get an ion thermal noise spectrum as well. And by combining these things, we can get the electron density, potentially the electron temperature, and potentially the Doppler shift of the ion population. And so those are our diagnostics. And what this requires is a specific antenna geometry. So what we want is that we want to minimize, let's go back to this, we want to minimize the shot noise signal. And the shot noise signal is just simply proportional to the density of the plasma and the area, the surface area of the antenna. So we want to make the surface area of the antenna as small as possible, but the resolution of this line, this feature here is a function of the relative length of the antenna to the Debye length. So we want the antenna to be as long as possible, but to have as minimal a surface area as possible. So that leads us to a wire rather than a cylinder. So we looked at this. We looked at a few different parameters. We looked at a 6 meter long tube, which is like did on stereo. We looked at a 30 meter long 1 inch rigid antenna, which is kind of like something like a tape measure kind of thing. And then we looked at some wires of different lengths. And we also looked at this idea of having, and Bill mentioned this already, a rigid antenna and a wire beyond that. So this is something where we could deploy a short antenna, a few meters long, let's say, and pull the wire out to the end of it and fly past Jupiter or past a KBO or something. So the spacecraft would be 3-axis stabilized. We could point it around. We wouldn't have any issues. And then when we go beyond Jupiter, for example, we want to spin up the spacecraft. I think all the in situ instruments probably want to spin up the spacecraft, and then we can deploy the wires out to their final length. So there is a possibility for this based on doing both 3-axis and wires. And okay, so here I've just run a few of these numbers. So this is the 6 meter rigid antenna for this is, I guess, local interstellar medium kind of parameters. And you can see that's the spectral peak there that we're looking for, that little bump, which doesn't appear in the total spectrum because it's dominated by shot noise. But if we go to a 50 meter wire, now the shot noise falls down because of the surface area of the antenna is smaller and the peak is resolvable. So at least in this case, local interstellar medium, we have, I think, a good chance of measuring the plasma density, and actually potentially this peak to plateau is a measure of the electron temperature as well. We'd have a chance of measuring electron temperature. And I should say that this density and temperature measurement is not a function, or not a strong function anyway, of the spacecraft floating potential. So it also kind of mitigates that issue. And then again, these are for outer heliosphere termination shot kind of parameters, where the peak gets to be barely resolvable, but maybe we pick it up. And then finally, this is the worst case, right? This is a part in 1,000, and this is with a long antenna. I think you don't really have much chance there. So as Bill mentioned, we'd want to have a sounder probably for the lowest density regions. Electromagnetic cleanliness, and Jim Kinnison knows all about this. So one issue is that this kind of measurement is if you go back to these features here, this is kind of this is more realistic. This is kind of a few nanovolt per root hertz noise level. This is what we did on Solar Probe. That's the preamp input noise, and that's kind of what you need to do this measurement. And of course, that's a very small voltage. And all the junk on the spacecraft, all the subsystems, the power supplies, all that sort of stuff will swamp this if you don't pay attention to it. So this is for example, on Solar Probe, this is our REO2 spec up here. This is the level that's allowable of noise. This is our preamp noise level, which is, you can see 1, 2, 3, 4 orders of magnitude lower. The way you overcome this is by controlling the frequencies at which this stuff operates. So on Solar Probe, Jim and his team did a bang up job of doing this. We have a really quiet instrument. It's also the case on stereo, where we just forced all the power supplies and chopping noise sources into discrete bands, frequency bands. And then we can make the measurements between those spikes, and it gives us a very quiet measurement. Okay, so a baseline instrument, this is less of a threshold. Bill showed you kind of a threshold. A baseline instrument, we'd have to have a 3-axis magnetometer. We probably want 2 of them. We have to specify some stray fields, a static stray field, a dynamic stray field at the sensor. And so we need to think a little bit about that. We're not there yet. I think the magnetometer would definitely want a spinning spacecraft as well. That's a good way to back out offsets, is by looking at the spin modulation of the total field, removing the spinning component. And ideally you'd want 2 sensors, and that would give you kind of gradiometry. It would let you see the spacecraft field from 2 different distances, which would help you understand the spacecraft field and help you have a higher quality measurement. Would also, of course, give you some redundancy. So, and I'll say something about that in a second again. Plasma wave instrument, I think we'd want, to first order, we'd want four wires, so we could do polarization and we could do direction finding, good direction finding. I think having bandwidth up to sort of a megahertz would be reasonable. As Bill pointed out, the interstellar medium emissions are going to be down at 10% of that or so. We can specify what a delta F over F, we need a kind of spectral resolution, what kind of noise levels we need. Those are kind of standard things. If there's an augmentation for a planetary flyby, or any augmentation that requires 3-axis stable performance, then I think we have to look at this kind of hybrid antenna configuration. So there we would have to have rigid antennas or remain undeployed through the flyby, which would be a huge bummer. And so I think a question there is, if there is a planetary flyby, for example, would we levy science requirements on that? Or would we just design to accommodate that mission phase? Because if we were going to levy science requirements, if we're going to say we have to do Jovian science, we want to capture Jovian science, that will flow through to, maybe we need a search coil magnetometer, would change our bandwidth, as Bill mentioned, of the measurements. It would probably change some of the instrument characteristics if we were going to have science requirements associated with Jupiter. If we're merely being capable of being deployed at Jupiter, that's different. So that's a question I think to think about. I think I don't need to talk about this too much, just to show you that we have this design for this is a little 1 meter stacer deploying. Just to show you what a stacer does, it just pops out of its own spring energy. It has no motor or anything. So one could imagine doing something like this, pulling a wire out here and then deploying the wire out after we spin up. We've done some work to estimate data downlinks. These are some numbers that David Malaspina ginned up. And I think the takeaway here is that an instrument like this is pretty capable. It'll produce a lot of data on the fly, and it'll have some capability to sum that, to average it, to find peaks, to histogram it on board in a simple way. And so our actual data link to the ground, or bits per second to the ground, is probably pretty flexible. I think this, in a nominal mode like this, we could easily generate 150 bits per second. But if we average more, we step down the cadence, throw out a channel if we're not using it, we could bring this down to, to bits per second. More bits is always better, but the instrument itself would have a lot of capability. Okay, so finally, I think I have a couple slides with some recommendations here. So what we're trying to do here, I think, is not over design it. We're not trying to, come to too much detail here, but we just want to make sure that that we can let Jim and his team know about what we think we need to do a successful instrument like this. So, an EMC program, we know we want to spin. We think we want long wires. We know we don't want long wires. so those are some things we want to get out to the spacecraft team right away. So for a radio and plasma wave instrument, again, we'd like some long wires, 50-meter wires. Probably they give us good radio measurements. They give us good density and temperature measurements, potentially velocity measurements. A hybrid situation could be, a hybrid system could be ginned up if we do Jupiter. A sounder, which is pretty easy, we just ping. This would maybe again be a benefit of having two pairs of antennas. We could ping one antenna and listen to the other one. Magnetometry, again, this is going to be a challenge, and I think we should maybe even encourage NASA to support some technology development here. So the good magnetometry is going to require a clean spacecraft, and again, APL knows how to do this. They've done it for us before. So we need a good spec on the static and dynamic fields. We definitely would benefit from spinning. We'd need to be on a boom. We need magnetometers on a boom, probably a long boom. Longer is better, 1 over r cubed in the case of a magnetic field. So, we've been talking about a 10-meter boom. If we had 2 sensors, we could do, gradient measurements of the spacecraft field. So this, for example, we do this on solar probe, and that helps us constrain the spacecraft field. And then importantly, we need to start thinking about how to get better signal to noise from a magnetometer. We recommend that we try to share an instrument clock between the in situ instruments. That we do this on solar probe as well, and it's great. It gives us not only a common time base, so it's if one instrument is sampling once a minute and the other one is sampling once every 51 seconds or something like that, it makes for a mess when you're putting data together. So having a shared clock is a good idea, and it also helps for the EMC issues. If everyone is on the same clock or on you can have some redundancy there, but if everyone's on the same clock, it helps for noise as well. And then again, some measure of redundancy or enhanced reliability. I think, if we have 2 magnetometers, they each have their own formatting board. We could do something like we did on solar probe again, where we have 2 power supplies. So there's a kind of an A side, and not a fully redundant A side and B side, but everything is operating. But if one of your power supplies goes down, you retain, for example, 1 magnetometer and maybe the preamps on 1 antenna pair or something like that. So you could have some capability for durability. And that's basically a summary of it all. So that's kind of where we are. I think we're not done. We've got more work to do. We've got to go through that STM with a fine-tooth comb, I think, and pull together map the instrument and its capabilities to those science objectives in the STM. Make sure we haven't missed anything. But I think at this stage, we kind of understand what would make for the bare bones of a good instrument. And that's my story.
Thank you, Stuart. I have one question. You mentioned the possibility of, or the value, I should say, of some tech investment in both quiet spacecraft and the magnetometer technology itself. I'm curious if, I know that on an annual basis, SMD kind of looks at what they should be investing in and what they might want to invest in. Do you know if this sort of investment's been proposed in the past?
I mean, there are people working on magnetometers. I know that. Typically, okay, so one issue is stability. And that can be, sometimes some of that can be addressed just by using an optical magnetometer of some sort of laser-driven or vacuum lamp-driven kind of magnetometer. Those things tend to be big or bigger, but I'm not sure they produce the kind of sensitivity that we need. So I don't know maybe if Art Posner's on. I think he was on earlier. He may have an idea as to what level headquarters NASA is investing in this. But I think it's a good goal that could be associated with this mission, to spend some money on developing a more sensitive magnetometry.
And Ralph asks, he says that Brian Anderson has suggested that based upon MMS performance, one might be able to get away with a boom of only 3 to 5 meters with a really aggressive mag cleanliness program. And has that changed?
Oh, I don't know if Brian's on, he could answer that.
I don't think Brian's joined us today, no.
I mean, it's a good question.
I can jump in here. So 5 meters is probably the very bare bones limit, according to Brian. And that's why we're sort of sticking in the model payload with a 10-meter boom.
I mean, the mass of The
Yeah,
mass
so
of the carbon. Oh, go ahead. Sorry. Oh.
Well, I was just going to say, this is Ralph. Yeah, this was a hallway conversation that I had with Brian some time ago, and we were talking about, getting well below 1/10 of a nanotesla, maybe down to 100th of a nanotesla. And at the time, Brian had said, well, with MMS, we did, we hit that and we were at 3 meters. And so what's the problem? You just need a really, really, really good mag cleanliness program. And I hadn't kept up with the thread on that, where you guys were.
Yeah, the problems are the weak fields out there. So the 5 meter is really the bare bones, I think.
I mean, I think
now we are at 10 minutes till the beginning of the next session.
Okay.
I want to make sure people do have a chance to stand up, stretch, take a bio break and whatnot. Perhaps if there's one more question out there, perhaps from an early career person. We have a good number of folks online who are either students or within 10 years of their most recent degree. Any folks from that category interested in weighing in or asking a question?
I have a question. So with the mag that you're suggesting, are we able to measure instabilities at the heliopause, like KH instability and Rayleigh-Taylor instability?
I mean, I would think so. I mean, those are large scale. Those are basically fluid instability. So they're going to be on large scales. And so when you look at those, like the data that Marav was showing, the integration times for those are probably days, right? So if you integrate a magnetometer like a Voyager magnetometer for a day or two, I think you can get the noise levels down. The question is, if we want to see things like, like Marav was showing, reconnection current sheets, things that are on current sheet timescales, it's going to be more challenging with what we have now.
All righty.
Thank you.
Thank you, Parisa, and thank you, Stuart and Marav and Bill and David and everybody else that participated. This has been great. So the next discussion is ENAs, and it's being held in a different Zoom room. So at the website, and I'll drop the link in here for everybody real quick. But you can always pull it right from the website as well. So I'm putting it into the chat. So if you want to copy that link, you can join the Zoom room for the ENA discussion led by Bob DiMagistri at 11:35. Thank you, everybody.
So Michael, we should leave this Zoom, is that right?
Yes, you should leave this Zoom, and when everybody's gone, I'll hit end, and it'll capture the recording of the whole thing. So
great.
Thank you, Stuart. Great job today, everybody.
Thanks, Michael.